Hello and welcome to Scientific Talk. What is time? An objective reality or a construct of our minds? Physics reveals its elasticity, while neuroscience shows how our brains shape its flow based on perception, memory, and emotion. In this video, by merging these perspectives, we uncover a deeper understanding of time as both a physical dimension and a human experience. Time is a concept deeply embedded in our lives, yet its nature is far more complex than we perceive. Both physics and neuroscience provide insights into how time works. Physics explores time as a dimension of the universe, while neuroscience studies how our brains experience it. By bringing these perspectives together, we can better understand the fascinating interplay between objective reality and subjective perception. In Einstein's theory of relativity, time is not fixed. It can stretch or shrink depending on factors like speed and gravity. For example, astronauts traveling at high speeds experience time more slowly than people on Earth, a phenomenon known as time dilation. Interestingly, our brains also perceive time as elastic. When people are in life-threatening situations, such as falling from a height, time seems to slow down. To test this, scientists conducted an experiment in which participants fell backward onto a net from a height. While falling, they were asked to read numbers flashing rapidly on a special watch. If time had genuinely slowed down in their perception, they would have been able to read the numbers. However, they could not. This demonstrated that the brain doesn't process external events more slowly, but instead, the amygdala, a part of the brain that processes fear, became highly active, enhancing memory and making the moment feel stretched. In other words, it creates the impression of slow motion by working differently during high-stress moments. So, why does our brain simulate slow motion? The brain creates this illusion of slower time for evolutionary survival reasons. In life-threatening situations, the brain's amygdala, which processes fear and emotional responses, becomes highly active. This leads to 1. Enhanced attention. The brain focuses intensely on every detail, allowing you to process more information in a short period. This heightened awareness makes the moment feel longer. And 2. Prioritization of memory. The brain prioritizes encoding vivid memories of the event, likely so you can learn from it or avoid similar dangers in the future. The increased memory formation stretches subjective time. In daily life, this phenomenon is mirrored in less extreme situations. For example, a car accident might feel like it lasts forever because your brain is processing more details than usual. On the other hand, time seems to fly when you're deeply focused, like during an engaging conversation, because fewer events are being processed. These subjective experiences mirror the flexibility of time in relativity, though they are rooted in neural processes rather than physics. Physics explains the flow of time through the concept of entropy. The universe naturally moves from order to disorder, giving time a forward direction. This is called the arrow of time. The brain experiences time similarly. Our sense of time's direction comes from how we store and recall memories. The hippocampus, a part of the brain critical for memory, organizes events in sequence: past, present, and future. Once a memory is formed, it cannot be undone, much like how entropy increases irreversibly. For example, if you drop a glass and it shatters, your brain stores this as a one-way event, an intact glass becoming broken. You can't mentally reverse the event, which mirrors the physical world where entropy always increases. But on a quantum level, time works very differently. Could this mean our sense of time is just an illusion? In quantum mechanics, time behaves differently than we might expect. The block universe theory suggests that past, present, and future coexist, challenging our belief that time flows. Additionally, particles at the quantum level behave unpredictably, existing in multiple states until observed. The brain's sense of time also involves a degree of uncertainty. For very short intervals, like milliseconds or seconds, the brain relies on estimates rather than precise measurements. Neural circuits, including the basal ganglia and cerebellum, work like internal clocks, but are influenced by context and emotional states. The brain's perception of time relies on internal mechanisms like neural circuits, but it operates with variability. In one study, participants tapped their fingers at regular intervals without external cues, revealing slight inconsistencies in timing. This variability was attributed to the basal ganglia's probabilistic approach to processing time, showing that the brain is not a precise clock but relies on approximations. Another experiment highlighted the cerebellum's role in timing precision. Participants with cerebellar damage struggled with tasks requiring high timing accuracy, such as pressing a button in sync with repeated tones. They consistently made errors, either reacting too early or too late, underscoring the cerebellum's importance in fine-tuning short-interval timing. Emotional states further influence time perception. When participants viewed emotionally charged images, such as a dangerous animal, they perceived the images as lasting longer compared to neutral ones. This distortion was linked to the amygdala, which interacts with the basal ganglia to heighten attention during emotionally arousing situations. These findings suggest that the brain's internal clock is adaptable, but influenced by emotional states and neural variability, leading to subjective distortions in how we perceive time. Imagine clapping along to a steady beat at a concert. If the music stops and you continue clapping on your own, your rhythm may slowly drift off. This happens because your brain's internal clock is influenced by slight errors in timing and the lack of external sensory feedback. These fluctuations, while minor, highlight the brain's reliance on estimates rather than absolute precision. This resemblance becomes clearer in experiences like waiting for a response after sending a text message. A few seconds of waiting can feel much longer because your brain is uncertain and focused on the passage of time, amplifying the delay in your perception. Physics shows that time and space are intertwined into a single framework called spacetime. Events in the universe are relative, depending on an observer's position and motion. Does our brain do the same? Similarly, the brain combines spatial and temporal information to create a coherent experience. The entorhinal cortex, a part of the brain involved in navigation, encodes where and when events occur. This integration allows us to link memories and actions to specific times and places. For example, when you watch a train passing, your brain synchronizes the sight of the train with the sound of its horn. Even though sound travels slower than light, your brain adjusts the signals to make them feel simultaneous. This ability mirrors the relativity of events in spacetime, where observers in different positions might experience the same event differently. But if both physics and neuroscience agree that time is not absolute, then what does that mean for our everyday experience? In physics, time can stretch near a black hole or pause for a photon traveling at the speed of light. Similarly, our brains construct time based on context, emotions, and memory, often creating illusions. For example, a phenomenon called the oddball effect occurs when a novel event, like seeing a bright flash of light, feels longer than it actually is. This happens because the brain devotes extra attention to processing something unexpected, stretching the perceived duration. Another example is watching a slow-motion replay in sports. Intense moments in the game, such as a goal being scored, feel longer because your brain processes more details, much like how time stretches in extreme physical conditions, like near a black hole. So, is time real or just a mental construct? Our understanding of time is shaped by both the physical laws of the universe and the workings of our brains. While physics reveals time's elasticity, direction, and connection to spacetime, neuroscience shows how the brain mirrors these concepts through subjective perception. Ultimately, time is not just a universal constant or a mental construct. It is a bridge between the external world and our inner experience, shaped by both science and perception. If you enjoyed the video, like, subscribe, and share your thoughts in the comments. See you in the next one.